Welcome to Shanti-Peace for Mathematics. In this lecture, we are going to discuss about the convergence of a sequence and series complex variable or numbers. You have know about what you mean by sequence of a numbers. For a real variable, the sequence of numbers generally denoted by x1, x2 up to xn and so on. And by notation, we may write this is as xn in this way, or in the round bracket xn we can write as a sequence of real numbers. And similar manner, the sequence of complex number generally they are denoted as z1, z2 up to zn and so on, and they are denoted as zn or in round bracket zn. Now the question is, whenever the sequence comes, the question is whether this sequence of complex numbers are convergent or not. So what should be the limit of this sequence? Let's talk about that. If I want to say that an infinite sequence z1, z2 up to so on of a complex number has a limit z if for given epsilon greater than 0 there exists n0 belongs to n such that mod of zn minus z less than epsilon for every n greater than or equal to n0. That means geometrically what does it mean is, for sufficiently large value of n, that's why it is n is greater than or equal to n0, the points of zn lies in any given neighborhood of z, that is this zn minus z less than epsilon. So if you can try to plot this is for understanding, let's say this is your z plane and this is the point z you have, and the neighborhood of epsilon neighborhood of this point will be this is the radius epsilon. Now what does it for large n? So there is z1 here, z2 probably here, z3 maybe here, but after that some points after n 0, every point should lies inside this epsilon neighborhood, that is zn0 is here, zn0 plus 1 is also here and so on. All other points are lies inside that. So given epsilon greater than 0, there exists n0 belongs to n such that for large n0 every point of this sequence zn is lies inside the epsilon neighborhood of z. That means zn is much closer to z as subscript, that is this n is increased. If n is increased, the distance between zn and z is small as much as you can. That is the meaning of convergence. Now if limit is exist, we'll say that zn n tends to infinity is z. This is the notation for limit exist. If the limit is exist, then the sequence zn, it's called convergent sequence. What do you mean by convergent sequence? That means this limit has to be unique. If the limit exists, the sequence is convergent. So let us have there is an property of this sequence, so that limit of convergent sequence of complex number is unique. Now to prove this, we have to prove it is unique. So for that I am assuming, suppose that there will be two limit of same sequence zn. So let's say suppose that z0 and z1 are the limit of sequence zn. That means by definition what we can say, for given epsilon greater than 0 there exist n0 and n1 belongs to n, because for z0 will have n0 and for z1 will have n1, such that zn minus z0 is less than epsilon whenever n is greater than or equal to n0, and zn minus z1 is less than epsilon whenever n is greater than or equal to n1. So what I will take is, I will take some m which is the maximum of this n0 and n1. Now I am starting with z0 minus z1, which is equal to, I am adding and subtracting zn here. So we'll have this, but using the triangle inequality we can write as, this is zn minus z0 plus zn minus z1, and that is, we can say that it is epsilon plus epsilon. So we'll have, say this is epsilon, 2 epsilon. So if you want here epsilon, you just adjust here epsilon by 2, here you will adjust epsilon by 2. So you will have here epsilon by 2, here you will have epsilon by 2, so this 2 will cancel out now. So you will have, this is equal to epsilon whenever n is greater than or equal to m, because this both statement are true, and since epsilon is arbitrary, mode of z0 minus z1 is 0, which implies z0 equal to z1. That means if limit is exist, then it has to be unique. We have started with 2 limits and we have shown that 2 limits are equal. So that means a limit is exist, it has to be unique. The second thing that we have, the next, is the very important results. So I am stating as a theorem. Suppose that Zn is equal to xn plus Iyn for n is equal to 1, 2 up to so on. For every n, this is true. And z will be x plus Iy if I consider. Then prove that limit of Zn will be z as n tends to infinity, if and only if limit of xn will be x as n tends to infinity and limit of yn will be y as n tends to infinity. So what is the meaning of this statement? This statement says that if the sequence of complex number is converged to z, then its real part will be converged to real part of a limit, and the imaginary part of a sequence is converged to imaginary part of the limit. So assume that limit of n tends to infinity, Zn will be z. For given epsilon greater than 0, there exists n0 belongs to n such that mode of Zn minus z is less than epsilon for every n greater than or equal to n0. This is by definition we can write. Now let us observe what is this side. So what we have given is Zn is xn plus Iyn and z is x plus Iy. So that will be xn minus x plus I yn minus y. So now what is this? Will be, I can write as xn minus x is less than or equal to mode of xn minus x plus I yn minus y. Why we can write this? Because of, we know that a real part of z will be always less than or equal to modulus of z. So due to that we can write this, and similarly we have imaginary part of z will be less than or equal to mode of z. So that is yn minus y is less than or equal to xn minus x plus I yn minus y. Now this quantity is less than epsilon whenever n is greater than or equal to n0. That means this quantity is less than epsilon whenever n is greater than or equal to n0, and this quantity will be less than epsilon whenever n greater than or equal to n0. So what we can say is for every given epsilon there exists n0 such that this quantity will be less than epsilon and this quantity will be less than epsilon. So therefore what we can say by definition, n tends to infinity, xn will be x and limit yn will be y as n tends to infinity. Conversely, suppose that these two conditions are satisfied. So this result was if and only if, as you have remembered, that if Zn is converse to Z, then it's converse to its real part and imaginary part. If the real part and imaginary part both are convergent, then we can say that the complex number is also convergent. To prove this one, we'll start again by definition. For given epsilon greater than 0, there exists n0 and n1 belongs to n such that mod of xn minus x is less than epsilon whenever n is greater than or equal to n0, and mod of yn minus y is less than epsilon whenever n is greater than or equal to n1. Now what I will take is, I will take again m equal to maximum of n0 and n1. So this statement is true for n less than or equal to m, and this statement is also true for n is less than or equal to m. We'll start with now Zn minus Z, because I want to prove that this Zn minus Z is less than epsilon. So as I've discussed above, what is Zn minus Z is xn minus x plus yn minus y that we have. Now by triangle inequality, what we can say, this one is less than or equal to mod of xn minus x plus mod of yn minus y. So this will less than epsilon plus epsilon, but epsilon plus epsilon will be 2 epsilon. So to adjust that as an epsilon, I am adjusting by 2 here. So that will be less than epsilon by 2 plus epsilon by 2, that is equal to epsilon whenever n is greater than or equal to m. As I told you, these two statements are true for any n greater than or equal to m. So that's why we have this. So therefore by definition, what we can say is limit of Zn is Z as n tends to infinity. So that proves that our objective says that if this sequence of a complex number is convergent, then its real part is convergent and its imaginary part is convergent. Its imaginary part is convergent, and converse is also true. That means a real part and imaginary part are convergent, then the sequence of a complex number is also convergent. With that note, or with that theorem, we'll have another theorem or property of this we can have is, if limit of Zn is Z as n tends to infinity, then prove that the first one, limit of mod Zn is mod Z as n tends to infinity, and second one, the sequence Zn is bounded. Now what do you mean by sequence is bounded? Sequence is bounded means there exists some m greater than 0 such that mod of Zn is less than or equal to m. For every n this is true. Then we can say that Zn is bounded sequence. So now to prove the first identity, just observe that this inequality we have already proved in one of the lecture, that modulus of mod of a minus b is less than or equal to mod of a minus b. So we will use this inequality to prove the statement that limit of mod of Zn is equal to mod Z as n tends to infinity. To prove this statement, we will use this inequality. So what is given is limit of Zn is equal to Z as n tends to infinity. So by definition, what we can say, for every epsilon greater than 0, there exists n0 belongs to n such that mod of Zn minus Z is less than epsilon for every n greater than or equal to n0. Now if you use this inequality here, what we can write is mode of Zn minus mode of Z is less than or equal to mode of Zn minus Z, which is already less than epsilon for every n greater than or equal to n0. So what we can say from this is, for every given epsilon greater than 0, there exists n0 belongs to n such that mode of Z minus mode Z is less than epsilon for every n greater than or equal to n0. So therefore, limit of mode Zn will be mode Z as n tends to infinity. So that completes the proof of that statement, that modulus you can take inside into the limit. The next one will be to prove that Zn is a bounded. So what we have is, for every epsilon greater than 0, there exists n 0 belongs to n such that mode of Zn minus Z is less than epsilon for every n greater than or equal to n0. So I'll start with that. I'm just writing is mode Zn will be mode Zn minus Z plus Z. I'm just adding and subtracting Z here. That we can write as mode of Zn minus Z plus mode Z. Since this statement is true for any epsilon greater than 0, so I will just take it epsilon is 1. So that will be less than 1 plus mode Z for every n greater than or equal to n0. So now there is no problem for n is greater than or equal to n0. So what I am taking as m, which is the maximum of Z1, Z2 up to Zn0 minus 1, and this one 1 plus mode Z, whatever the value of this, whatever the value among this n0 value, whatever the maximum, I am taking it as m. Now for that, what we can say is mode of Zn is less than or equal to m for every n. Now I can say, so therefore sequence Zn is a bounded sequence. That proves the statement which we have. So the next result is, the sum of two convergent sequences is convergent, product of two convergent sequences is convergent, division of two convergent sequences is convergent. So for that I am taking with, let Zn n converge to Z as n tends to infinity, and Wn will converge to W as n tends to infinity. Then the first one we can say that limit Zn plus Wn will be Z plus W as n tends to infinity, and if it is minus here, you will have minus here. The second one is Zn into Wn is Z into W as n tends to infinity. The third one is limit C into Zn as n tends to infinity with C times Z, where C is a constant. And the fourth one we can write is division, limit Zn upon Wn will be Z by W, provided W will not be 0 as n tends to infinity. So we are not going to discuss the proof of this, but this is very important result to check whether the given sequence is convergent or not. Now we'll have an example. So in two ways, that the sequence Zn equal to minus 2 plus I minus 1 raised to n upon n is converged to minus 2. Also prove that the principal argument of Zn is also sequence. So I am just saying it is a sequence does not converge to principal argument of minus. So that is the statement. You have to show in two ways whether this series is converged to minus 2. The first way is by definition, and the second way is with the help of the real part is convergent and the imaginary part is convergent, and then we can say that the sequence is convergent. So these are the two ways you can show that this given sequence is convergent. So we will show that for given epsilon greater than 0, there exists n0 belongs to n such that mod of Zn minus Z, what is Zn is given to you is minus 2 plus I minus 1 raised to n upon n. So it is minus 2 plus I minus 1 raised to n upon n. Minus of minus 2 will be less than epsilon. We have to show that is for every n greater than or equal to n0. This is our objective to prove. So I am starting with for given epsilon greater than 0 and I am considering what is Zn minus Z. So you just observe that what will be this Zn minus Z is this minus 2 will cancel with this minus minus plus 2. So what is this? Zn minus Z will be minus 1 raised to n upon n into I. The mode of I is 1 and mode of minus 1 raised to n is also 1. So that's why this is 1 upon n, and 1 upon n is always less than 1 for every n greater than or equal to 1 upon epsilon. So what you need to take, your n0 will be box of 1 by epsilon, where what is this box is box of as is denoted as the greatest integer function or largest integer function of x. So whatever the largest integer of 1 upon epsilon is there, that I am taking as n0. So therefore what we can say is for given epsilon greater than 0, there exists n0 which is this box of 1 upon epsilon such that mod of Zn minus Z is less than epsilon for every n greater than or equal to n0. And hence we can say that this limit of this Zn will be minus 2 as n tends to infinity. Now in the second way, if you want to prove what is Zn is given to you, the Zn is given as minus 2 plus I minus 1 raised to n upon n. So what is given is minus 2 plus I minus 1 raised to n upon n. So what is the real part? I am saying is xn, that is minus 2, and yn will be minus 1 raised to n upon n. Now where is this x? These are the two real number sequences, and you know that the xn is a constant sequence which converges to minus 2, and yn is a sequence as n tends to infinity, this will converge to 0. So therefore xn plus Iyn, that is your Zn, will converge to minus 2. So this is another way to prove that the given sequence is converged to minus 2. Now the second argument or second question was asked is what will be the argument, principal argument of the Zn, and whether it is converged to argument of minus 2 or not. So for that, let us calculate what will be the argument of Zn. So principal argument of Zn is tan inverse of yn upon xn. So that is tan inverse of minus 1 raised to n upon minus 2 into n, because yn is this, that is minus 1 raised to n upon n, and xn will be minus 2. So I am just substituting that value here. So that will be tan inverse of minus 1 raised to n plus 1 upon 2n. So now where is this sequence is convergent? So you just look at this quantity, that is argument of z 2k, that means even power where it is converged to. So you can say that if it is 2k, then it is tan inverse of 2k plus 1. This n is 2k, so it is 2k plus 1, so it is minus 1 upon 4k, because 2 2s are 4, so we will have minus 1 upon 4k, tan inverse of 1 upon 4k plus pi, because it is minus sign. Why because of minus sign? Because your x is negative, because your x is minus 2. And what will be the y if z is nk, it will be a minus number, so it is also negative. Okay, so this is a negative number, and x and y both of them are negative, that means they are in the third quadrant. If it is in third quadrant, whatever the angle is there plus pi will be added into this. So this will be the angle, if I can say that angle is theta, so it is pi plus theta because these points are in third quadrant. So for that it is there. Now for argument of z 2k plus 1, that means it is odd power, then it is tan inverse of what you will have if you substitute here, that is 2k plus 1 plus 2, that is minus 1 raised to 2k plus 2 upon 2 into 2k plus 1, that is then even number, and this is also even number. But if this is even number, then it will be a minus minus become plus, so it is tan inverse of 1 upon 2 into 2k plus 1. Now what will be the argument that you will have? Now your x is minus 2 and y will be positive because that is minus 1 raised to even power is there. So if you consider this is x and y axis, and your x is negative, y is positive, that means x is negative here, y is positive here, that means they are in the second quadrant. So whatever the angle of this, that angle is this one, and so I can say that that angle is the, if this is theta, that is this angle, so it is pi minus theta. So that is, I am subtracting pi from it, so it is tan inverse of 1 upon 2 plus 2k plus 1 minus pi, that we can have. So we can say that where is this first is convergent, the first is convergent, that means the limit of argument of z to k as k tends to infinity will converge to pi, because you can see that this is argument of z to k. You can say that the k is infinity, then it is 1 upon infinity, that will be 0, tan inverse of 0 is 0, so it will converge to pi. And the second one, limit argument of z to k plus 1 as n tends to infinity will be minus pi. So therefore what we can say is even terms will converge to pi and odd term will converge to minus pi. So therefore the given sequence, that is argument of Zn, is not convergent. Now the next thing we have is about the infinite series. So the, you know that the sum of sequences is known as a series. So that is summation of n running from 1 to infinity to Zn will be Z1 plus Z2 up to so on. This is known as a series. When I can say that this series is convergent, if its sequence of partial sum is convergent, so if I define the Sn, where I am denoting as capital N, which is n running from 1 to capital N, Zn, which is nothing but the sum of first n terms. Now this will be the sequence of complex numbers. So what is S1 will be Z1, S2 will be Z1 plus Z2, S3 will be Z1 plus Z2 plus Z3, and so on. Sn will be Z1 plus Z2 plus Z3 up to Zn. So, and this is the sequence of complex number. If this sequence of complex number, that means if this Sn, it is known as a partial sum, is convergent, then series summation of Zn is convergent. And if this sequence of partial sum limit will be S as n tends to infinity, then we can write that summation of Zn is also S. It's also converges to S. So That's why we can have the definition of convergence. This also you have studied in your F5 BSc class. So I'm just recalling what you have studied there, and here just the variable there we have studied is real number, here we have a complex number. Now we'll have one next theorem which based on the series. Let I'm considering Zn is xn plus iyn for n is 1 to up to infinity. S I am defining as capital X plus I capital Y. Then prove that summation of Zn is as n tends to 1 to infinity if and only if summation of n running from 1 to infinity xn will be x and summation of yn as n tends to 1 to infinity will be y. That means if you have a series whose real part, if you have a series which is convergent, then its real part is convergent and imaginary part is convergent, and converse is also true because this result is if and only. So the proof of this result is very simple, means it's come from the sequence proof which we have discussed above. So I'm considering the partial sum of summation n running from 1 to infinity Zn as summation n running from 1 to n Zn as Sn. Now what is this Sn? Sn is summation n running from 1 to infinity 1 to n Zn. Now you just observe that that is nothing but the summation 1 to n xn plus iyn. So what we'll have, this one is nothing but the summation n running from 1 to n xn plus I summation n running from 1 to n yn. Now you just use the result which we have discussed earlier, that limit of Zn is z as n tends to infinity if and only if limit of xn is x as n tends to infinity and limit of yn is y as n tends to infinity. So using this result that we have, what we can say is if limit of Sn is s as n tends to infinity if and only if we have xn is limit of xn is x as n tends to infinity and limit of capital Yn is y as n tends to infinity. What is capital Xn will be this value and capital Yn is this that we have. So what we can say is xn is converse to x and yn will be converse to y. So therefore we can say that summation of Zn is s if and only if summation of xn will be x and summation of yn will be y. Next definition we have is absolutely convergent. So when I can say the series Zn n running from 1 to infinity is absolutely convergent if the series mode of Zn as n tends to infinity is convergent. Now what is this series? Is nothing but the mode of Zn. You know that if it is x plus iy, then this will be nothing but the square root of xn square plus yn square. So this is nothing but the a series of real number. So if this series of real number is convergent, we can say that the given series is convergent, and that we can, from this we can state a one line that every absolutely convergence of a series implies convergence of a series. So every absolutely convergent series is always a convergent. So what we can start with, suppose summation of Zn is absolutely convergent series. So if I start with mode of Zn, that is less than or equal to summation of mode Zn, by triangle inequality we can say that n running from infinity, and this is convergent. So by comparison test this is also convergent. Or if you can say this also, this way also we can state mod of xn is less than or equal to mod of xn square plus yn square, and mod of yn is less than or equal to mod of xn square plus yn square. Where this we can write. So by comparison test in here we can say that the summation of mod of xn square plus yn square is given, it is absolutely convergent. So therefore summation of mod of xn is convergent, and similarly here if I use the comparison test, summation of mod of yn is convergent, and you can say that summation of xn is less than or equal to summation of mod of xn. This is already convergent, so that's why this is convergent, and same way yn is also convergent. So by comparison test, finally what we can say is the real part is convergent and the imaginary part is convergent. So this will imply summation of Zn is convergent. So that completes the proof of statement that every absolute convergent sequence is convergent. The converse of this result is not true. So at the last I am giving you as an exercise that you can find out the example for which the converse is not true. That means find out the example where the summation of Zn is convergent but summation of mod Zn is divergent. Okay, so I am giving you an exercise that find the example. With that I am stopping here. So if you like this video, please press the like button. If you have any question, comments or suggestions, please drop down in a comment box below. See you in next video. Bye bye. Sayonara.